Problem 1. The parametric equations x is equal to t squared plus 1, y is equal to t cubed minus 3t. Part A is the graph, which you'll see that solution in the PDF that you downloaded. Part B is the horizontal velocity. Think of velocity, that's the derivative. So we're going to take the derivative, but since it's in the horizontal direction, it's the x portion of your parametric. So dx dt, you have x is equal to t squared plus 1. Simple problem, dx dt is 2t. Plug in your negative 1, and your horizontal velocity is negative 2. The vertical velocity, again, it's a derivative, but this time in the y direction. So dy dt is 3t squared minus 3, and you plug in t is equal to negative 1, and you get a vertical velocity of 0. Speed is defined to be as the square root of dx dt squared plus dy dt squared. So we found that dx dt was 2t, dy dt is 3t squared minus 3. So we're going to square that 2t, square that 3t squared minus 3, and then plug in the value of negative 1. And I would typically do that without working out the algebra in that problem. So you put in negative 1 where you have that 2t, you get negative 2 squared. And when you have a negative 1 in there for the 3t squared minus 3, you'll get 0. And so you take that square root of negative 2 squared, which is 4, turns into 2. In parametrics, to measure the slope, which is dy dx, you simply put dy dt over dx dt. You can almost see how the dt's would cross out. So dy dt is 3t squared minus 3. dx dt is 2t. You plug in a negative 1, the derivative, again, which is the slope of the curve, would be 0. The second derivative is a little more challenging. Again, from before, we had dx dt equal to 2t, dy dt being 3t squared minus 3, and the first derivative, which is the slope, is 3t squared minus 3 over 2t. Now, before going to the second derivative, what I always do is try and simplify the first derivative. So you have 3t squared over 2t minus 3 over 2t when you separate the fractions. Reduce those, and you get 3 halves t minus 3 halves t to the negative 1. So when I'm going to find the second derivative, which is acceleration, I'm going to take the derivative of the derivative, but with respect to t on the top. On the bottom, you're going to take the derivative of x with respect to t, or the horizontal velocity. Taking the derivative of the derivative, looking up above, 3 halves t becomes 3 halves. Negative 3 halves t to the negative 1 becomes, when you kick the power front, plus 3 halves t to the negative 2. Down below, dx dt is equal to 2t. Plug in your negative 1, and the second derivative at t is equal to negative 1 equals negative 3 halves. In order to find a horizontal tangent, it's easier than you might expect. When a tangent line is horizontal, the slope is going to be what? And of course, the answer to that question is slope is equal to 0. So we just find the derivative, which we've done a couple times now, to get 3t squared minus 3 over 2t. Now, fraction is equal to 0 when the top is equal to 0, but not the bottom. So you set 3t squared minus 3 equals 0, t squared is equal to 1, which implies that t is equal to plus or minus 1. Again, we're looking for points, so you plug t is equal to 1 into x is equal to t squared plus 1 and y is equal to t cubed minus 3, and plug in negative 1 into the same parametric equations. And you have 2 points, 2, negative 2, and 2, 2, where the tangent line is horizontal. And finally, finding a vertical tangent. Slope here, when you have a vertical tangent, the slope is undefined, it's an impossible slope. So when you find that derivative, 3t squared minus 3 over 2t, to make a fraction undefined, you set the bottom equal to 0. So 2t is equal to 0, t is equal to 0, plug in that value up above, and you get the point 1, 0.